All right, we just did a problem using collisions and different kinds of collisions. We talked about that in an earlier video. A collision that we used in the last problem was a perfectly inelastic collision, stickage, good word, sticking together, finding the final velocity of the two at the end. This is a little different problem. It is a momentum problem. I'll show you why, but this is a different problem. This is problem number 5, Marty. Remember Marty? Marty McFly from Back to the Future? Hello, McFly, hello. Okay, Marty is not Back to the Future. He is in the future because he's in a spacecraft out in space. So Marty is floating in space and must get back to his spacecraft. That's problem number 5. So apparently his tether line's been cut. Oh no. No panic, no panic. He has a wrench in his hand. He is working on the spacecraft or something. And the spacecraft, let's say, is over this away, okay? Over this away. To my left and or you're viewing right. Then Marty says, I got this. I know 2 things. I know Newton's third law, and I know conservation of momentum. I'll get back to my spacecraft. How's he gonna do that? Holding wrench. Throw the wrench. And we will be able to move in the opposite direction. For every force, or every action, there's an equal opposite reaction or force. So therefore, that's Newton's third law. Or conservation of momentum. How conservation of momentum? What are you talking about? How is that the same thing as Newton's third law here? Good question. Good question, Wilma. Now, what's my momentum right now? I'm Marty, by the way. Marty. Only Marty would wear a shirt like this, right? Marty, wrench. Thank you. Thank you. I was acting. It took me years to get that down. Nailed it. I'm talking Academy Award coming up for that acting job. No momentum. Nothing's moving. I'm not moving. Wrench isn't moving. So before we do anything here, there's no momentum. The system, me and the wrench, Marty and the wrench, have no momentum. If I throw the wrench, it gets momentum because it's moving. And I will move as a result. Right now, we'll just think of action-reaction. Conservation of momentum, we'll show you why in just a second. But I'm moving as well. I have momentum. So, wrench has momentum, I have momentum. Well, that's both things have momentum, so clearly the conservation of momentum isn't happening here, right? Because you started with 0 momentum, and now both things have momentum. So that's the conservation of momentum doesn't apply here. That's out the window. No. Remember a couple of problems ago, the impulse problem? When one thing goes one direction, then goes back the other direction, we have to distinguish between the directions by giving one a negative, negative. Very good, Jane. A negative. And that means that positive and the negative opposite directions are going to cancel each other out. The total momentum before and after is going to be maintained. That's a conservation of momentum. It's a law, people. It's a law. We ain't breaking it. Not today, maybe. Maybe tomorrow, but not today. We ain't breaking that law. So, no momentum. Throw. Momentum. Momentum is a result of throw. One's going to get a positive, one's going to get a negative. Now, the wrench is a lot lighter, so it goes a lot faster. Marty is a lot heavier, it doesn't go as fast. They do balance each other out. If we multiply their masses and velocities, one's a positive, one's a negative, 0. Before 0, after 0, conservation of momentum. This is a momentum problem. It's not a collision. We're not smacking into things and bouncing off or sticking. Not a collision, but momentum still applies here. So let's go ahead and do this as a momentum problem. That's why it's in the momentum section. So number 5, Marty's floating in space. Marty has a mass of 100. Marty is not moving yet. Velocity of 0. This is momentum before. We know has to equal momentum after. So Marty, total momentum of the system. The system is Marty and the wrench. That's the system. System momentum is Marty, got it, wrench, got it. Mass of 2, velocity of 0 before we throw it. Then we throw it. After we throw it, we want to figure out Marty's velocity. So we know Marty after is still Marty, okay, unless maybe an asteroid came along and took off his leg or something. It's still Marty, 100 kilograms. We don't know his velocity. In fact, that's what we're trying to find here. The wrench, though, we know is going to be moving at 40-something miles an hour. It's 20 meters per second. It's over 40 miles an hour. So Marty's given a good throw. in the opposite direction. Ooh, opposite direction. Somebody's got to get a negative. It doesn't make any difference who you give a negative. That's irrelevant. So to your left, I will give that a negative. That's the wrench. So you get the negative. It doesn't matter. You can switch them and you're still going to get the same answer. If you don't believe me, try it. Okay, go ahead. Try it on your own. And do the math. This is a big fat 0. This is 100x. And that is a plus negative, so it's plus negative 40. Switch this, isolate x, so add 40, we get 40 equals 100x, x divided by 100, x is going to be equal to 0.4. 0.4 meters per second. Now, 0.4 meters per second is not very fast. I mean, it'd be fast for a snail, I suppose, or a turtle, but not for, you know, we're used to. It's like that far per second. So Marty gives that wrench. The wrench isn't very heavy. It's let's just say heavy. We're in space, not very massive. And so therefore, give it a good throw, 40-something miles an hour. You're moving it about this fast, about 40 centimeters per second backwards. But hey, you get back to your ship, you know. If the ship is this way, if it's not this way, I just threw it in the wrong direction. It'd be really stupid. But yeah, here I go. There I am. Oh, boom, just bumped into it. Whew. Oh, I'm so glad I made it. The ship's over there. I threw it that way. Makes sense. Okay, so we solved this. It's going to be 0.4 meters per second. And we used momentum conservation. Now, this is the same idea. I used a person in a wrench as a cannon firing a cannonball, or an artillery piece, like a howitzer firing a shell, a military shell going boom, that direction. What are you going to get out of that? You throw the projectile this way, and what happens to the cannon or that howitzer? Boom, goes the opposite direction. There's action, reaction. There's recoil. That's a momentum situation, just like this one is. We're just not using a wrench and Marty. We're using a gun, or in this case, a cannon and a cannonball. Okay, let's look at a gun and see how this applies. And we can actually do this a little quicker. Now, I did this out with momentum before equaling momentum after. Okay, I did the whole thing out. We can shorten this up a little bit. Maybe you can see it already, but here's how. We'll say I've got a gun. Now, we shouldn't be talking about guns in education, right? So let's make this Cupid's gun. He's upgraded finally to whatever 20-something century we're in. I don't know, was it like the 28th century or something like that? It's like 27, 22. I don't know what year it is. I'm a mess. So Cupid's finally upgraded. Forget the bow and arrow, Cupid. Come on, get with the program, okay? He's got a high-powered love rifle, which fires love bullets. Okay, so we'll put a little heart in here. See, that's the bullet, ready to go. A little heart. Isn't that nice? You get hit by Cupid firing the little heart. You fall in love with the next person. I think that's how it worked with the Cupid thing. So Cupid upgraded. We have ourselves a gun which fires bullets of love. Okay, a little weird, but whatever. It works. After the action. So before we do anything, we haven't fired the gun yet. There's no momentum. Ball's not moving. Gun's not moving. 0. Afterwards, the bullet, there's our heart, nice, goes flying out of the gun at a high velocity. It's not very heavy and it moves very fast. The gun's going to have to recoil in the opposite direction. Much heavier gun won't recoil as fast. All right, but those two, if we multiply the mass times velocity of the gun and the mass times velocity of the bullet, they've got to equal each other. So we can set up a situation like this where we get action, reaction, and recoil. Just take the two momenta and set them equal to each other. And you can kind of cut out a little bit of that other math that I had to do. It was easy math, but when we have a situation like this, recoil, just set the two, momentum going out, momentum going back, equal to each other, solve. So if I knew this bullet was 5 grams, that's 0.005 kilograms. It's moving at 1,000 meters per second. That would be a high-powered rifle shot. And Cupid's upgraded, so he's got the good stuff. Okay, so that would be 0.005 is my mass in kilograms. Velocity 1,000. Here, let's say the mass of the rifle is 5 kilograms. The recoil velocity can now easily be calculated. So that is 1, 2, 3, 1, 2, 3 is equal to 5. Okay, 1, 2, 3. So 5 divided by 5, because we have to divide by 5 to get velocity here. This is 5 divided by 5. Velocity is 1. Our kickback velocity, recoil velocity, is be about 1 meter per second. Your shoulder's there, so and you go, you laugh at that. You go, shoulders and okay. So there you go, much quicker action reaction. I had a college roommate who was in graduate school. He was a business major, and I thought this was a very good question for a business major. Okay, yeah, I'm judging. Yeah, I am. And he asked me, he said, hey, we're watching the movie Aliens. Aliens, second one with Sigourney Weaver. Well, oh, Sigourney Weaver. It was awesome. Watch it. Okay, and there's this one scene where they show the spacecraft with the colonial marines going to save the poor civilians on the alien-infested planet. And they show the engines of the spacecraft firing up. They get boom, glow bright. And the acceleration of the spacecraft is the opposite direction. And he asked me this question. He said, how is it, in the middle of nowhere space, can a spacecraft accelerate if there's nothing to push against? And I looked at him, I said, that is a good question for you. It's just so mean. And I said, that's a very good question. And I said, the answer? Well, now you have two ways to answer that. You could say, well, action, reaction. If there's a thrust going out the back, there has to be a reaction of something going forward. That's the way life is. It's Newton's third law. Or you could also say conservation of momentum. The mass and velocity of the gases coming out of that spacecraft, the engines in the back, have got to be equal to the mass times velocity of the spacecraft going forward. Gases go out really fast. The mass of the spacecraft very heavy, so the gas will produce a forward velocity, actually acceleration, but forward velocity in response to that. So we have two ways to answer that. Okay, we're going to take a quick break, and then we're going to come back and do the last